Hello everyone, welcome to my short introduction of geometry algebra. The goal of this series videos is to do rotation of vectors, any vectors in 2D and 3D and n dimension with the same formula. If you don't know what vector, what is a vector, don't worry, we will cover this soon. So if we compare geometry algebra to linear algebra and quaternion, geometry algebra tend to give us intuitive formula, and this formula also will apply to to any dimension, not just 2D or not just 3D. It will be the same formula. In order for us to do the rotation, so in this series video we will learn vector space. However, we will not go into the precise definition of a vector space, but we will learn the idea of vector space, which is most important in my point of view. Once you know the idea behind the vector space, if you open any linear algebra book, the vector space definition makes sense. And then we will learn a wedge product. Then we will learn a geometric product. We will use it to derive the geometric product table, and we will use this table to learn projection and rejection, and then also reflection and rotation of vectors. However, there's many type of GA. We will only focus on something called VGA, which the most basic GA when one start to learn a geometry algebra. And the vector in VGA represent direction. VGA stands for vector-based geometry algebra. The vector represent a direction, doesn't represent position. Very important. If you want to learn, and we will only use it for rotation. If you want to learn translation, you can go to VGA, and the vector will represent plane. And if you want to learn, there's also a CGA, which represents a sphere. If you want to learn these two, you can go to vivector.net, which I will put the link in the description below, but I can also write it here, vivector.net. Yeah, and in this video I will only assume that you know the cosine or sine, that you know that before. Before we jump into vector, we want to talk about direction. We want to learn about direction, and we can represent direction as an arrow. And if we have a coordinate like this, then we can describe an arrow with a number with x and y. But in this course, we don't want to do that because with the coordinate, we are bounded with the origo. And we will consider this arrow and this arrow is the same as long as they point to the same direction and have the same length, even though they don't start at the same point. They don't have the same starting point. So we will try to describe direction with our coordinate. But without coordinate, how can we describe direction? We can actually describe direction with respect to another direction. For example, if you have an arrow, if you have an arrow pointing in this direction, let's call this A arrow, and another arrow pointing on this direction, let's call this B arrow, and we can have a new direction called C, like A plus B. Then is A. We just write the arrow A and plus B again. This is A and this is B. And then we just connect the tail to the head, and this is C. Then we can have, for example, not necessarily 1A, 1B, but have 2A plus B, right? Then it will be, let me move this a little bit. No, let me move this a little bit up. Then yes, then we can have this 2A. Like this is A, this is also A, and also 1B, and that will be our W. And we can also, given a direction, given an arrow, which is also pointing to some direction, we can also define the opposite arrow, which, for example, if you're looking here, the arrow A, we can have a direction pointing in the opposite. The arrow pointing in the opposite direction. Let's call it minus A, right? Then we can have minus A. We can have the A arrow plus minus A arrow equal to 0, because when they plus together, they just cancel out. You can try it like this, then going back, then they just cancel out. There's also one thing that if, for example, our C is pointing like this, right? Like here, like the guy here. We cannot describe C with A alone. So A is pointing on this direction. You can only scale A bigger or smaller or point to opposite direction, but you can never describe C with A alone. So we have in 2D, we have to describe in 2D, if two arrows not pointing into the same direction, we can describe any direction with respect this two arrows that is not pointing to the same direction. So that motivates us. We can describe all the direction in 2D with only two set of an arrow, and we call them bases. So in 2D, I write it more. Let me write it more. In 2D, we have bases. Like this, we first construct our first arrow is pointing to the right. It has length 1. So we just, this notation denote the length is equal to 1. And also the second arrow is pointing up. It has also the length 1. And importantly, this E1 and E2 are 90 degrees to each other. And then we can use these two arrow. One is pointing to right, one is pointing to the up, to describe all the arrow we have described before. We can also describe since for example, if we want to describe C, we have described C with A and B, right? Okay, I will just draw it here. We have described C, the arrow C with A and B. So if we can describe A with this E1, E2 and B with this E1, E2, we can also describe C with E1, E2. So the A1, if you just look at it, then you will see that it's roughly 1 E1 plus 2 E2, right? And then if you look at B, is equal to 1 E1 plus, no, is minus E2. Then C, if you substitute them into this equation, then it's easy to get just equal to E2, E1, and these two get cancelled out. So that concludes that we can describe in 2D, we can describe any direction with the basics we define that has two direction pointing into different, two arrow pointing into different direction. Now we talk about vector and vector space. We will not dive into the precise definition, mathematical definition of vector space. You can find it basically on any linear algebra book or on internet. But majority of them don't actually talk about the main idea or don't directly talk about the main idea of a vector space. But once you understand the main idea of vector space, the definition of vector space is quite obvious. So what is the main idea of vector space? The main idea is sometimes we don't always work with a single number. Sometimes we work with an object. And we need to find a good way to scale the object and to get another similar object. And we need to find a good way to add the object together and to get another similar object. So in our case, our similar object, we have a set of similar object. Our similar object is a 2D arrows. They are all arrows, but they are also somehow different because each one have individual length and direction. So we need to define how can we do the addition. How can we add those arrows together? So let's say we have, I think we have talked about this before, that we have arrow A plus arrow B. Arrow B is pointing like this. So we define C equal to, C is defined, arrow C is defined equal to arrow A plus arrow B is like this. Then what arrow C is just connect the tail to the head. Yeah, so that is the arrow C. One thing to notice that the arrow is not a number. And since, as we said before, we don't use coordinate, so they cannot be expressed as a number. And now we know how to add those arrows together. And we also need to define how we scale the arrow. For example, if we have A like pointing up, this is A, then if we want half arrow A, it will be like this. This is how we scale the arrow and get another arrow, get the scaled arrow. One thing to note is that we plus this arrow together, we get an arrow, and we scale the arrow, we still get an arrow. So it's still inside our set with our set. So of course there's some more requirement to a set to be a vector space, but we are not going into the detail of it because it's not so important in this series. The main idea is just remember that the vector space let us work with object and number, not just number alone. So of course the object can be number, but not necessarily number. In our case, our object is an arrow. or many different arrows. Yeah. So since our arrows will satisfy our addition, scaling, and will satisfy all the definition in the vector space you find in any linear algebra book. So we can call this arrow vector. So we will just call this vector, we will just call the vector A, and here's the vector B, and here's the vector C.